Yes.
Alrighty. Hi everybody, I'm KellyDine, and this is my discrepant event on convection. As you can see, I have two able-bodied, maybe not so willing students with me today. Over here I have older son Stephen, and over here I have younger there's a smile, non-smiling son Alex. Stephen will be a junior this year taking AP Biology. He's already completed honors chemistry and honors biology. Alex will be a freshman this year, and he is entering honors biology. Last year as an 8th grader, he had general science. Today we are talking about convection, and in front of me I have the materials needed for my discrepant event. I have 4 equal glass bottles, 2 with red water that is very hot, so hence red signaling hot, and then 2 bottles of blue water, which is very cold. I also have my red and blue food coloring that I use to tint the water. I have 2 containers, equal size containers, filled with sand. One is filled completely with sand. The other is only filled halfway. These are to demonstrate density of the hot water and the cold water. And finally, as part of the discrepant event, I had to use 2 flat cards, one of which is an expired credit card, the other of which is our handy-dandy Woodrow Wilson $10 iTunes card. So, we are going to get to work. First things first. Boys, let me tell you what I'm going to do. I am going to carefully place a red bottle on top of a blue, and on the other side I'm going to place a blue bottle on top of the red. Meaning I've got a hot water over top of the cold water, and a cold water over top of the hot water. What I'd like you two to do for me is do what we call a pairing event, where you're going to think, you're going to share. We don't have any writing materials, you're just sort of going to discuss your ideas about what you think might happen when I remove the plastic card between those 2 bottles, with the red over top of the blue, and with the blue over top of the red. All right, Stephen, any ideas?
Wait, so
what I'm going to do is I'm going to put a hot water over top of the cold,
okay,
with a card there to separate them, and then a cold water over top of the hot.
Oh, so you're gonna
with a card there to separate them. Without making a mess.
Oh.
And then I'm going to remove the cards, and we're going to see what happens to the water. The only thing I can tell you for sure is that the water in the bottles is identical. So the 2 blue bottles are identical, the 2 red bottles are identical. I'm not pulling any tricks on you here. What do you think? Any ideas on what might happen? What do you know about water?
Well, heat rises.
Okay, heat rises.
So I'm guessing that the red water that's on the bottom of the one stack will rise to the top and mix, and the other one won't mix.
Okay. Fuzzy, Alex, do you have any ideas here?
Same thing, I guess, except the other one won't mix.
You think which one won't mix?
The one with the hot water on top.
You think the one with the hot water on top won't mix?
Yeah. Because
of Stephen's idea that heat rises?
Yeah.
Okay. What do you guys know about density? What is density?
Density, the more dense something is, the more tightly packed together it is.
Okay.
So usually it means it's heavier.
Okay. So take a look at those 2 jars of sand there, Alex and Stephen.
Mm-hmm.
Alex, which one is more dense? Which is more tightly packed together? Okay. And which is less dense? So if the sand in there represents molecules, tell me about the molecules in there, either Stephen or Alex. Alex, why don't you try?
The molecules in here are tightly packed together.
Okay.
The molecules in here are more spread out because they have more room.
Okay, good. Which do you think represents hot water and which do you think represents cold water? Any ideas based on your prior knowledge?
Cold water because cold is tightly packed together.
Oh.
Hot water because it's spreading around.
Stephen, what do you think?
Same thing.
You think the same thing?
The computer shut off.
What? It's still recording.
Oh.
It's still recording, but...
Yeah, that's okay.
Okay.
Okay, so next we are going to go ahead and try our experiment, okay? Now bear with me. I've tried this once. I've tried this twice. The first time I made a mess. The second time I was successful. Would you like a towel?
No.
In case I'm a little messy.
I left my phone upstairs, so I'm okay.
Okay. All right. Here we go. So first things first. We're going to do this.
Ew.
we're going to do this. We're going to do this. And if a little water spills out, I was assured that that's A-okay. Just do me a favor, guys, and don't bump the table, okay?
Achoo.
I chew. Then, I'm going to do this. I'm going to do this. Alrighty. We are set. Okay. How are we looking in this camera? Can we see what's going
I
on?
can see the blue and the red bottles.
Alrighty. Okay. Tell me again, guys, what did you think was going to happen on this side with the hot water over the cold? Don't touch.
Not too much is going to happen until as the bottles start getting towards room temperature, the water will start to mix. But at the initial, not too much is going to happen.
Okay. And in here, Stephen, you said you thought heat would rise.
Yeah. So the cool will come down and try to mix with the heat to they'll both turn purple, kind of.
You think so?
Probably.
Alex, what do you think?
I agree with Bubba.
You agree with Bubba? Why?
It seems common.
Wait,
sense.
it seems like common sense.
Yeah,
Is that because he's older than you?
probably.
He's done this before, maybe?
Yeah.
Okay. But we did say the heat rises, right?
Mhm.
So, Stephen, if you're thinking the heat rises, or Alex, if you think heat rises, what should be the case over here?
Then the red water will mix with the blue water.
You think the red will mix with the blue?
Yeah.
Going this way?
Yeah.
Okay. All right, guys. Are we ready for the first one?
Mm-hmm.
Okay. And there we have it. Okay, give me some observations.
It's
Not mixing.
Okay. Anything else at all going on?
Not really.
No.
No?
There's not really any mixing now.
Okay. All right, you ready for the second one?
Mm-hmm.
Now I want you to take a look and make some observations as we do this. See if the water seems to rise. The heat, the hot water. See if that seems to rise, okay?
Mm-hmm. Or if the cold one seems to fall.
Mm-hmm.
Probably the second one.
Wow.
The cold seems to fall.
What's going on there?
The heat's rising.
Well, no, the more dense stuff, which is the colder water, is coming down into the lighter stuff, which is the hot water. So it's mixing.
And it's pushing the hot water up.
Is that what it's doing?
Mhm.
Yeah. And why, Alex? Why is it pushing the hot water up?
Because the cold water is more dense.
Okay.
And the volume of the container's got to kind of stay equal.
Excellent. Nice job. Good work, guys. Okay, let me ask you a couple questions about all this then, okay? Alrighty. The speed of mixing in a convection cell, we're calling this a convection cell, right? We're talking about convection, is proportional to the temperature difference of the liquids. What does that mean?
That means that the difference between the temperatures of the two things makes the bigger the difference between the two temperatures means that they'll mix faster.
Okay. So what if, Alex, both of them were just sort of lukewarm? What if the temperatures were the same? Would we have any process of convection going on?
No.
Would there be any change really in the density of either one?
No.
So what would happen?
They would stay the same.
Okay. Alrighty. Is it more appropriate? Now, you told me at the very beginning that you thought, lean that way for me. You told me at the beginning that you thought that heat rises.
Mhm.
What's it more appropriate to say now?
That cold.
Cold falls and pushes the heat up.
Right. And what's that called when it pushes the heat up? What's another word for that?
Convection.
Begins with a D.
Dilution.
Displacement.
Good. Displacement. That's all right, Alex. Stephen's had more time than you. Good job. Displacement. Okay. Why does a given volume of cold water contain more mass than the same volume of hot water?
Because it's
Cold.
tightly packed.
Okay, good. So think about it this way. In the spring and in the fall, think of a lake, maybe like Lake Erie. Okay? In the spring, February and March, what's on the top layer of Lake Erie?
Ice.
Okay. Is ice more dense than liquid or less dense than liquid?
Less dense.
Less dense.
Okay, and Alex, well, how do you know it's less dense?
I read it somewhere.
You read it somewhere. What else? What about ice in a glass of water? What does ice do?
Rise to the top.
It floats, right?
Yeah.
So can you say it's less dense than liquid? Okay. Now think about this. The ice melts. Right as the ice is melting, where is the coldest part of Lake Erie?
At the bottom.
No.
The top.
Did the bottom freeze at all through the winter?
Okay. No.
Okay. So where's the coldest part of Lake Erie?
The top right away.
Okay. What's going to happen just as that ice melts and that cold water on the top? What's it going to do?
Drop.
What do you think, Alex?
Drop.
Drop. And do what?
Begins
with a D.
Displace
Yes, displace what?
the water underneath it.
Yes! And guess what else is laying down there on the bottom?
Warmer water.
Fish.
And what's in that warmer water?
Fish.
Okay, and what are the fish eating?
Food.
Food.
Nutrients,
Nutrients.
right? So when the cold water drops, it's going to displace down there, and those nutrients are going to come back and disperse and circulate through the water for those aquatic organisms, right? Okay? Likewise, think about the fall. So you've been swimming in Lake Erie, right? When you swim in Lake Erie in the summer, where's the warmest water? When it's shallow or out there where it's deep?
Shallow.
Shallow.
Okay. So, summer turns into fall. Temperatures dropping, right? What's going to happen as the water is just about to freeze in like December and January? Where's going to be the coldest part?
At the top.
Okay, what's it going to do?
It's going to drop.
And
Going to bring the other water up.
it's going to displace,
Gonna
right?
keep-
And again, what's the organisms going to do in the fall?
They're going to recycle like nutrients.
Mhm.
And they're going to go down.
Right. So that's how a lake can permanently stay healthy and active, right? Does that make sense, Alex?
Mhm.
Okay. Fantastic, guys. Any other questions that you have for me?
I'm observing bubbles rising to the top of the left.
Okay. Where'd the bubbles come from? What are they, Stephen?
Wait, where?
I observed a bubble go from here to here.
They're air bubbles, and they're probably coming in through gaps in the seal.
So, Alex, what does that tell you about air bubbles and their density?
They're more dense than. Wait, no, they're less dense than the water.
Okay. One last question for you before we finished. What happens if I use salt water? Would that affect the experiment?
Yes,
Why?
because salt is more dense than some waters.
Stephen, what would you say?
Yeah, salt is more dense than water, and that means that the salt water would mix and drop, but displace the regular water because it's more dense.
Okay. All right. Any last words for the camera?
Hi, Mom.
Okay, everybody, we're signing off. Thank you for watching my convection displacement experiment.
I think that's very cool, Alex. Observated.
Is observed a word?
Most people would
Okay,
simply
where do I hit
observe.
stop
Stop.
at, Stephen?
To the right.